the next week's plan is going to introduce the next step is to start talking about the discrete time Fourier transform. So what I would like to do is just give you a basic framework, and from that we will start to build in the next class. So our goal now is to start to look at the definition and the properties of the discrete time Fourier transform. Discrete time Fourier transform. And if you remember, this comes from the property of the eigen functions of discrete time systems. We showed that e power j omega naught n is an eigen function. So basically we are looking at some way of analyzing the behavior of the discrete time system, and that's how we come up with this expression. Okay, we also gave an interpretation of the representation of periodic signals, but again we will develop it completely in this context. So if I have a discrete time sequence x of n, discrete time sequence x of n, then I can define the discrete time Fourier transform. Discrete time Fourier transform. So basically this is the Fourier transform, and I will get x e of j omega to be equal to summation n equal to minus infinity to infinity x of n e power minus j omega n j omega n. Okay. Now a transform, what does this transform tell us? It says x of n I am mapping into another function in the transform domain, call it the Fourier domain or frequency domain, and it is a function of omega. So what are some observations about x e of j omega? Okay, x e of j omega is a continuous function of omega, correct? Because omega is a continuous variable, continuous function of omega, correct? And omega does not go from minus infinity to infinity. I mean basically, but it has got omega is a periodic function. In discrete time, omega is a periodic function with period equal to 2 pi. Period equal to 2 pi. So which means that x e of j omega is also a periodic function. Periodic function. Okay. Now, the original x of t, supposing this x of n was obtained from a continuous time signal xc of t. Was the spectrum of the continuous time signal periodic? No. But remember, when we went through the process of sampling, what happened? You started to produce multiple copies, and what was the period of the periodic of those repetitions of the spectra? It was in multiples. So in the process of conversion from xc of t to xs of t, okay, this xs of j omega was periodic was periodic, and the period was equal to omega s, because you saw repetitions of the spectrum, right? That was what. Now this is what got converted to x of n. This is what eventually got converted to x of n. X of n. Okay. So in the process of sampling, we got that, and what we are saying is the frequency Fourier domain representation of this is x e of j omega, and this has to be related to this, right? Because basically that was a continuous time version of the sampled signal. This is the discrete time version of the sampled signal. The Fourier transform of both of those must be the same, and that is why we now are seeing that, okay, x e of j omega is a function of omega, omega is periodic, x e of j omega is periodic, but it is not, there is no, it is completely consistent with the fact that xs of t was also periodic. Okay, because we have mapped it into the discrete time domain. So how did we map it? Remember, we said this is going from minus omega s by 2 to omega s by 2, and the next copy Nyquist trampled k equal to 1. Okay, this is centered around omega s, and this is how we obtained it. Now, if I were to look at it in the discrete time domain or convert this, the conversion is omega s times Ts is equal to the discrete time frequency. Okay. So, basically what is this? This is 2 pi by Ts times Ts. This is omega s. So, basically, so this will become 2 pi, this will become pi, this will become minus pi. So, this is for xe of j omega. Xe of j omega will be now in the range minus pi to pi, and then you will see repetitions at multiples of 2 pi. Exactly the same spectrum will now show up in the discrete time domain. So, this is what xe of j omega is going to look like, and we will now that you have understood the process of sampling, you know where it is coming from. But this portion of the justification is not needed if you look at it purely in the discrete time domain. Okay, this is more for understanding purposes. Even if you did not have that background, you can still say if you define xe of j omega in this manner, xe of j omega will be a continuous function of omega. Omega is a periodic function because it's got period equal to 2 pi. In discrete time, omega is a periodic function. And therefore, the xe of j omega will also be a periodic function, right. So, that is what we understand, and that is what we will apply. So, now the inverse Fourier transform. How do I go from xe of j omega to x of n? So, we will give a definition and then we will justify it through a proof. So, x of n is equal to 1 over 2 pi minus pi to pi xe of j omega e power j omega n d omega. Okay, so, we are saying that if this is xe of j omega, you can do the inverse DTFT. Okay, this is Fourier inverse in going in the backward direction. Okay, now how do we prove that this is the inverse Fourier transform of the of this particular sequence? So, basically we got the forward transform defined. How do you verify that this is the inverse process? So, that is something that we will try to establish. But before we get to that, can we write down some additional observations about xe of j omega? Now, x of n can be real valued or complex valued. Real valued or complex valued. Okay, it can be anything. Regardless of whether x of n is real valued or complex valued, xe of j omega, what can you tell me about xe of j omega? Basically, it is a combination of complex exponentials. So, xe of j omega is complex valued in general. Okay, under very unique cases, you will find that xe of j omega is real value, but most of the time, so let us say that this is in general, this is the case. Now, if it is that case, then the Fourier transform or the Fourier spectrum, okay, or call it the Fourier spectrum or the DTFT Fourier spectrum or DTFT, all of these we say are referring to the same thing, can be represented as xe of j omega as a real part and an corresponding imaginary part, xie of j omega. Okay. We can also represent it in terms of a magnitude and phase. Magnitude xe of j omega e power j times argument of xe of j omega. Okay, that will be the ratio of the tan inverse of the imaginary part divided by the real part. Okay, so we call this as the magnitude spectrum. Okay, the Xe of j omega is called the Fourier spectrum. Magnitude of Xe of j omega is called the magnitude spectrum. Magnitude spectrum. Okay, and this is called the whole thing, argument of Xe of j omega. This whole thing is called the phase spectrum. So, magnitude spectrum, phase spectrum, both of which are derived from the real and imaginary parts, and so a discrete time sequence can be represented in terms of Xe of j omega, and Xe of j omega is a complex quantity in general. So, you can think of it as real part and imaginary part, or magnitude and phase. Magnitude and phase is what we will often look at and then say that this is what we are looking to utilize. So, for example, we have already used this as a statement without even giving the definition of it. So, if I want to consider a low pass filter, okay, and I specify that my frequency response XLP of j omega magnitude, if I say that is going from some cutoff frequency to another cutoff frequency, omega minus omega c to omega c. We used this notation. Remember, we said that a reconstruction filter will be a low pass filter which goes from minus omega s by 2 to omega s by 2. Without explicitly stating what did we use, we used the magnitude spectrum of the magnitude spectrum is what we have used to specify a low pass filter. Okay. Now, typically when you want to specify a filter, we will specify both magnitude and phase, but predominantly for the filtering operation what is of most significant importance is the magnitude spectrum. So, if you notice that we have already started to use the concept of a magnitude spectrum without explicitly calling that, but we will now develop it. So, another important result which we already have is that any LTI system is always represented by means of an impulse response, right? Impulse response which is h of n. Now, we can say that this LTI system can also be represented by the discrete time Fourier transform, which is given by h e of j omega. We have another domain in which we can analyze the behavior of the discrete time system. Okay. So, let me give you an example what we mean by that. So, if I have an example, h of n is equal to delta of n minus 2. H of n is delta of n minus 2. Now, we know that what will this do? It will produce an output which will be convolved with h of n. If this you are convolving it with this LTI system, then it will produce for you x of n minus 2. Now, this delta function can also be visualized in the following manner. Okay, what is its response? H e of j omega summation n equal to minus infinity to infinity h of n e power minus j omega n. In this case, n is the h of n is non-zero only for n equal to 2. So, basically we get e power minus j 2 omega. H e of j omega, this delay is a LTI system whose impulse response is delta of n minus 2, whose discrete time Fourier transform is given by e power minus j 2 omega. Now, what is the magnitude of this? H e of j omega equal to 1. Okay. And what is the argument of h e of j omega? Equal to minus 2 omega. Okay. So what we say is a delay function, a delay operation does not change any of the frequencies. All frequencies at the input will appear at the output with the same gain. He of j omega is equal to 1 for all omega, right, from anywhere from minus pi to pi for all omega. Okay, so basically this is for all omega, and the argument of He of j omega varies linearly as omega. Okay, so again we have not really talked too much about the phase, but if you want to understand what the phase is, this is a good way of understanding the phase. Okay, so the important thing for us to note is that we can represent any LTI system in terms of the impulse response. We can also look at it in terms of the discrete time Fourier transform, which will also give us some very unique insights. Okay. Now, in the last few minutes, what I would like to do is to prove that the inverse Fourier transform is the correct representation that we have obtained. Okay. So, this is the proof of the inverse Fourier transform, of inverse discrete time Fourier transform. Basically, that we have, what we have is a Fourier transform pair. So, we are given that xe of j omega is given by summation k equal to minus infinity to infinity x of k e power minus j omega k. This is given to us. Okay. Now, suppose the inverse transform relationship does not give me x of n, but gives me x hat of n. So, let us say, suppose x hat of n is equal to 1 by 2 pi integral minus pi to pi xe of j omega d omega. If we do not know whether it is x of n, so we say it is some x hat of n is the e power j omega n d omega. That is the expression that we have. Okay. So, now let us see how we can systematically go forward. This is 1 over 2 pi integral minus pi to pi. I am going to substitute the expression for xe of j omega from the equation number 1. So, basically what we will get is summation k equal to minus infinity to infinity x of k e power minus j omega k. Okay. This is the expression for xe of j omega. We have e of j omega n d omega. Okay. We have an integral from minus pi to pi, we have a summation from minus infinity to infinity. What I am going to do is interchange the order of the summation and the integration. So, what I get is 1 over 2 pi, let me write it with the same colors, 1 over 2 pi, okay, the summation comes on the outside, summation k equal to minus infinity to infinity, minus infinity to infinity, x of k, the integral is with respect to omega. So, the x of k can come outside the integral. So, you have x of k followed by the integral. The integral is minus pi to pi e power minus j, or you can take it as e power plus j omega n minus k d omega. Okay. And this has to be evaluated, readily evaluated. You can easily evaluate this expression, and this integral has got the following result, that it is equal to 1 if k equal to n equal to 0 for k not equal to n. Okay, so basically this is the effect of the of this integral. Okay, this 1 over 2 pi has to go in along with the integral. Okay, this 1 over 2 pi is sitting here. Okay, that's this integral is equal to this is the expression for that. All right. So then we find that x hat of n, this becomes summation k equal to minus infinity to infinity x of k delta of n minus k. That is what is equal to 1 if k equal to n, and so basically when you do this summation, then what you get will be this delta function will be non-zero only at k equal to n. So what you will get is this is equal to x of n. So in other words, x hat of n, which was the we said was the was the result of this integration, actually turns out to be the same as x of n, which then is the proof of what we are looking for. So the discrete Fourier transform pair, we can formally, you can say that this is the Fourier transform pair. The forward transform is xe of j omega, which is given by summation n equal to minus infinity to infinity x of n e power minus j omega n. This is the discrete time Fourier transform or the forward transform. Okay. And x of n is obtained as 1 over 2 pi integral minus pi to pi x e of j omega, as we have just now proved, e power j omega n d omega. This is the inverse DTFT or the inverse transform. Okay, so this is the Fourier transform pair that we are going to be studying. We are going to be looking at very carefully, looking at the properties. We are going to look at how to calculate the discrete time Fourier transform, how to calculate the inverse discrete time Fourier transform. All of these are going to be very interesting and useful results for us, because this is what is going to give us insight into the frequency domain representation and behavior of the discrete time signals and systems that we have studied in the time domain and we have been looking at so far in the time domain. So let us stop here, and we will pick it up from here in the next session, where we will quickly summarize the discrete time Fourier transform and then start looking at examples on how to compute discrete time Fourier transform, what are some of the properties of the discrete time Fourier transform, and how we can use it to study digital discrete time signal processing as a powerful tool for many applications. Thank you.